Yeah, I'm leading a research group on deep learning and Bayesian modeling at Aalto University, and we are mostly doing sort of the mathematical stuff, development of new algorithms and methods, so using different benchmark tests with small images and text data and so on. So I won't have that many great demos about our own work, but instead I wanted to tell you about what is deep learning in general and in the context of understanding images, since this is the visual form. So in the context of images, deep learning is known as convolutional networks. So let's try to get you there. What is it? What is it all about? So if we have a look at what has been happening in computer vision, and specifically the image classification task, there was this big yearly competition called ImageNet, where you have a million images labeled in 1,000 different categories, and you are supposed to learn from this data, and then when receiving a new image you have never seen before, you have to know in which category it belongs to. And this is on the bottom you see the performance, the error levels of the winning competitor on different years, and the performance has been sort of staggering somewhere, but then came deep learning convolutional networks in 2012, and things started happening really rapidly. So actually the whole field of computer vision is now turned upside down, because everyone since 2013 already, most of the top competitors in this competition, for instance, had switched to deep learning. So things are happening rapidly right now, and things in AI which have been sort of the Achilles heel in AI are starting to become possible. For instance, we have a data where we have the text captions for images, so we can now learn to, when given a new image, describe the contents using text. So in these examples are new images that have never been shown to the convolutional network, and it's able to tell what's in the image. And you can also visualize that when the system is saying the word frisbee, for instance, in the top left corner, the area where the system is looking at is in the image is where you can see the actual frisbee. So things are happening rapidly. This is work from my former student, who's now a professor in New York University. Also, I want to take a visualization example. You see so there's a photograph on the top left corner, and then the idea was in this work to take the textures and colors from different paintings and try to use the contents from the picture, the photograph, but then use the artistic style of some artist or some painting, and you see the end results that this can be done automatically nowadays. So both of these examples are from this year, so it's really happening now. So what are convolutional networks? What is deep learning actually? So the traditional way of doing, let's say, image classification would be to take an image, so the pixels, as Kalle was explaining, it's a huge table of numbers, and how to get anything out of it. You first do some feature extraction. For instance, features such as, okay, there are lots of horizontal edges in this area, or there's some texture of grass in this area. Different kinds of features, and the traditional way was to create these features by hand. So you had an engineer who was coming up with different kinds of features and then combining them into high-level features and so on. But now it's all done automatically. So you give lots of data and you let the deep learning system learn those representations that it wants to. So now we replace the feature extraction part of the learning process by automatic learned representation. So the machine is learning how to represent the data. So in this case, it might be that, so this is the end result after the training, that the first level, low-level features might be some edge detectors and some color detectors and so on that are applied all over the image. And then what's called deep learning. It means that the model is deep. You have several layers, one after the other, and each one receives its input from the previous layer. So then it goes to the next level, and you have on each level you have a nonlinear transformation of your data. And once you have enough layers, the representation is highly nonlinear and can do very complex things. And then you train your classifier on top in case of classification. So the classifier on top could be this, like the Sigmoid classifier that Kalle used as an example. So, but the idea is that if you would apply the classifier to the pixels directly, it wouldn't work. But if you do it in a deep network of multiple stages and you learn each stage separately, then you can do much better. Okay, so let me go into even some more technical details, like what is each layer actually doing, and why is it called a convolutional network? So if you take an image on the left and you convolve it, so this convolution operation, it's this kind of a star, and you convolve it with a small filter, you might get features such as the horizontal edges or vertical edges out of your image. And you could do those filters you see on the top by hand, but you can also learn what to use. So you basically initialize them randomly and then let the data decide what will be the final filters like. So let's take a simple example of classifying handwritten digits. This is a standard benchmark in deep learning. It's a small data set, so you can run many experiments easily. So, and I'm visualizing some results, the resulting network after training. So you'd have small images, 28 by 28 pixels that contain just one handwritten digit. So the first layer in this deep network would be a convolution layer, and on the right you see the weights of the network after training. So you have 9 different filters. Each of them is 5 by 5 pixels in this case. And once you do the convolution over the input image, the resulting signal is there in the middle. So different filters concentrate on different aspects. For instance, the filter in the top middle is looking at diagonal edges that are this way, and it finds four of them in this digit 8. The next layer would be pooling. So typically those convolution layers increase the number of channels that you have. So let's say RGB image would be a 3-channel image. Now it's a 9-channel image after all those filters. So you want to reduce the resolution by pooling. In this case, we are doing a max pooling, which works nicely in the context of classification to decrease the resolution. And then you go further up next you can have another convolution layer, and again increasing the number of channels that you have, in this case from 9 channels to 16 channels. And then the number of filters is much larger already, and the representation is starting to become, in the middle, top middle, you see that the representation of the data is starting to become more and more abstract. It's more and more difficult to understand what is it actually doing. And you could go on for 10 to 40 layers even, and then you can have really abstract things like what does love look like or something. Or okay, but in this case we have a second pooling layer, and then the classifier on top, and it's the sigmoid classifier more or less. So the sigmoid classifier just takes the final signal in the middle, and I'm showing here all the parameters, all the weights in the network, and the resulting classification, the probabilities of it belonging to different classes from digit 0 to digit 9 are here in the top middle. And in this case it was very certain that it's the handwritten digit 8, which is the correct answer. So now when you have data, you can train all those filters, all those weights that I've been showing on the right to maximize the performance on your training data. And the more training data you have, the better model you will get. So that's somehow the short story of what the convolutional networks are doing. But it's also interesting to have a look, to get a bit more understanding of what is happening by working your way backwards in this model. So let's say we try to investigate what is happening here. Like, what is this representation actually telling us? And let's look at an individual unit, the one that is circled red in this activation on the top level. And let's investigate this, what the unit is doing by computing the gradient of that unit's activation with respect to the input image x. We consider the image just a vector. So it's a vector x. And the gradient, so the derivative, as you remember from school, you do it by using the chain rule. So you use the chain rule to get the gradient over all the different layers of your model, and you can visualize the signals all the way back down. I didn't mention some of the details like the non-linearities there, but for instance, here you see that the gradient is pretty sparse, that when you put the gradient through the maximization process, only the unit that was the most active out of those 4 that were combined together will get the gradient, and so on. So you actually get a better intuition of the equations, the math behind there, if you work your way backwards. And then once you get to the pixel space or the input data space x, vectors x, you can, when you visualize it, you can notice that the unit was actually paying attention to this the top loop of the digit 8. So that's what it was looking at. And we can repeat this with this process with a bit larger networks and more realistic images. And for some, let's say, some unit on layer 2 of a big network, we can find the data examples that activate this unit the most. So so now for each unit we have found, or Tyler and Fergus found 9 data examples that activate this unit the most, and they do this the same visualization of how would it look like in the input space. How would you change the input such that the activation of the unit changes the most? And then you can see what is one unit in your network looking at. And on layer 2, there are relatively simple features like some circles or edges or colors, textures. But once you get higher up, the features become more and more abstract, like looking at different grids where you have some whiter grid on some darker background and so on. Might have some unit looking at legs of some animals and so on. And here's my favorite unit on the top right corner, looking at cars and women. So that must be a male neuron, male unit. Okay, but then you can ask the question, like, what is this whole layer looking at? Like, if you're not interested in one individual neuron, but the whole layer, let's say the second layer in our example network, and we can ask that what kind of a change in the input would activate the whole layer more. So we take the gradient of the norm of the activation on the whole layer H, and take the gradient with respect to the input image. And again, we work our way backwards through the model, and we see that, okay, it's looking at this digit 8. So in this case, it's not very meaningful, but if we do it on a big image, then we can actually do some nice art. We can generate hallucinations. If we change the input image slightly towards what some layer is looking at. So this artificial layer is paying attention to something in this image. And we can emphasize that something a little bit, and then we can repeat the process. So actually, starting from something random, we can get this neuron hallucinate stuff. And so here we take a really big network that was trained in Google with many layers. So you start from here, you put the input image here, you work your way through all those layers. Blue color is for convolutional layers and so on. And from the top you continue here and go through all those layers, and then you have the classification as those, and you do the classification actually 3 times. I don't go into details about this structure, but let's have a look at the video of what happens when you start to hallucinate. What are different layers paying attention to in this network? So in this video, every couple seconds, you change to another layer and see what is it looking at. And then there's some zooming happening, so things change. And yeah, deep learning is a very good fit to parallel computations or running things on GPU. And it's a pretty heavy process to train some kind of a big network, so you actually need quite a lot of GPU time. For instance, generating this video, the whole video is 9 minutes, so it took something like 1 month of GPU time to generate it, and that's after training the model, and that was done by Google using 1,000 computers, I think. So yeah, and working your way backwards in the model is not only for art, but you can actually do something useful with it. And our group, we have a new system where we're not doing only classification, but we are at the same time doing a secondary task of denoising the image. So we artificially inject noise to the image, and while we are classifying it, we also try to reconstruct the original image. And this way, on some benchmark tasks, we have gotten the state-of-the-art classification results. And especially interesting is the case where we have a so-called semi-supervised learning case where we don't have all the labels. So let's say you recall the image with the blue and red dots. Let's say we only have a couple of labels, a couple of blue and red colored dots, and we have lots of unlabeled data. So we only have a circle but no color for it. So how can we use that data? So in our model, we can still do the denoising task. And because we are using the same network to do both the denoising and classification, all that unlabeled data is also supporting the classification. So in this benchmark task of this handwritten digits classification, we've been with only 100 labels, we can reach results that a couple of years ago took 50,000 labels to reach. So it's working nicely. So what's the time? Am I done?
We have to finish.
Okay.
Are you finished?
I'm finished.
Okay.
Okay. Thank you.
You are both Finnish and finished. We're in Gothenburg, people. You should be able to think that's funny. But okay, anyway, Jesus, that's really. Your eye tried to find things, so the eyes go like this within the image. It's almost like a type of torture when you do this. Tell me more about the usage. Where in which fields do you feel that that you're going to be able to get any use of this?
Yeah. So let's say we go into video data. So no one will be able to label by hand, let's say, thousands of hours of video, like each frame, like is the right answer is like this. But then we might have a small amount where we have this hand labeled data. But then we have a large amount of videos where we only use we only have the content and not the right answer. So these kind of cases where we have less labeled data, we can use this working our way backwards and doing the denoising to help the classification task. So.
It's interesting because you work. It's the whole chain from the very non-image, just the letters and the numbers, and you walk up through to the very simple images and all the way up to the very extreme. It must be fun to work with the whole chain like that.
Yeah. So developing new algorithm methods, we of course first concentrate on the very simple small tasks where you can try things immediately. You don't need to wait 1 month to get the results. So it would be impossible to develop new things with the large scale things. But of course, seeing the results of the big tasks are the most interesting ones. So.
So do you connect with other research around the world, or do you sit your team sit alone in your chamber in Aalto?
Yeah, actually, actually, I'm just coming from DTU Copenhagen this week, and we have close collaboration with University of Montreal, Professor Joshua Bengio's group. So something like 5 visits last year and so on.
Okay.
So it's deep learning seems to be very open, that even the industrial researchers are publishing their software and papers and results. So it's a collaborative effort. No one could solve it alone. So.
Oh, okay. So let's see if we have we have time for one question or so from the auditorium. Anyone who wants to? Oh, we have Elina. Hang on, we're going to give you the microphone.
So what happened 4 years ago when this convolutional networks and deep learning came? What enabled it?
Yeah.
What made it possible?
What made it possible? So I'd say it's the 3 things. So first of all, developing the algorithms. That deep learning is a new buzzword, but basically it's an extension of artificial neural networks that have been studied for 70 years or so. But there was some development there. Now there's lots of quick development because it's so hot. But also big data. So having all the access to open data is very crucial. And the third thing is computational power. That is deep learning is a very good fit to parallel computing. So we can run things very easily on GPUs, for instance. And that's without the computing power we couldn't actually do the same things. So someone actually took some of the algorithms from 1980s and just run them on today's hardware. If they would have done the same computations in the 80s, it would still be running. I'm sure that it's so much faster now. So they got much better results than what was published in the 80s. So it's a big part of these developments.
Interesting. Okay, thank you. Thank you also for your presentation.
Thank you.